Okay, thanks everyone for coming. And those of you who are not in the United States may have adjusted your schedule by an hour to participate. So welcome to the new era of online seminars. As topology seminars around are being canceled, we are talking about perhaps ramping up some of our activities. So you'll see perhaps see some announcements about that sort of thing, maybe some adding additional talks to the schedule and so forth. But in any case, for today, we have Bjørn Dundas, who will tell us about Matific Hochschild homology.
Well, thank you. And it's good to be here in the Corona age. So today I'm going to talk about a joint project with Mike Hill, Kyle Ormsby, and Per-Arne Östberg on Matific Hochschild homology. And so what is it all about? The abstract is that we do the usual stuff in Hochschild homology, but we do it in the Matific situation. And in the end, we're going to have an answer that does, of course, correspond to Böck's test calculation in the stable homotopy situation. But why do we do this? First and foremost, we do this because if we want to understand E-infinity ring spectra in a Matific context, and we do want that, then one of the first things we should try to understand is exactly Hochschild homology. But I must admit that my personal interest is more because such a calculation sheds light on the topological case. And of course, this is a very small piece in an ongoing project, most of it, which is much more impressive than what I'm going to talk about today, on trying to use Matific methods to gain insight into things that we do not understand fully in the stable homotopy situation. So, but I'll come back to that at several instances as we go along, but just formally, Hochschild homology is usually given by the following formula. If C is an S algebra, where S is something, then it is given by the tensor of C with C over C op tensor C over the ground ring S. I'll talk a lot more about that in a moment, but just so that we have it clear. But today, S is going to be the Matific sphere spectrum. And I say that it's over an algebraically closed field of characteristic different from 2, but I think we should be very safe if we say that it is the complex numbers. That's given why I'm mostly interested in this, that should be more than enough. And C here is the mod 2 Matific Eilenberg-MacLane spectrum. And this is something that has been thought about for quite a while, and we have had some fanciful approaches to this, but it turns out that the most primitive approach actually works wonderfully. We just muddle through as usual, and what happens is that, of course, in the Matific situation, you have some complications because there is much more stuff going on. But on the other hand, it's way more rigid. So all that stuff actually is controllable. And I should say that some of you who might have heard this talk some time ago, well, the current approach is way more primitive than the fanciful ideas that we were using earlier on. But also, I should also say that the approach that we had at a certain stage was crucial, at least to me, in order to guess how the simple approach was going to work in the end. So let's get down to it. And I try a small didactical device here. The right-hand column here is mostly going to just store old stuff in case you forget it. That's one of the things that's irritating about a Beamer talk, is that it's so easy that you just flip the page and you forget everything that happened there. So apart from this one time where I build the right-hand column and one more time later on, you can just ignore the right-hand column unless something you have forgotten. But now let's start. So what is Hochschild homology? So if we start, and I do this because I want to insist what Matific Hochschild homology is in the Matific context. I don't want this to be open for discussion, what I mean. So if you have a model category or an infinity category or something like that, then you have an initial object and you have a final object. And with that in mind, we do define the zero sphere in there simply to be what you get if you take 2 points or final points and glue them together along the initial. And you take the 1 sphere to be what you get if you glue 2 points along the 0 sphere. Of course, the points that you glue together, they should probably be fattened up. So everything here is in the derived sense. And so on. And you get the higher spheres and you get all sorts of cell complexes, but everything is built out of the initial and the final point. So I just stick to that from now on. And in particular, when C is a commutative S algebra in some context, and we'll talk about 3 different contexts today, the 0 sphere, so these are commutative S algebras over a fixed S algebra C. So the initial object is S itself and the final object is C. So the 0 sphere, and of course the coproduct in commutative S algebras is called tensor over S, is just C tensored with itself. And in some situation that's called the dual Steenrod algebra, and I might lapse into calling it that in general, but it's just a 0 sphere. And the 1 sphere, and now you recognize the formula, the 1 sphere is just what you get if you take 2 copies of C and tensor them together over the 0 sphere. And that is what I'll call Hochschild homology. And the op that was on a previous slide has vanished because we're in a commutative setting. So to my mind, Hochschild homology is just the 1 sphere in the category of commutative S algebras over a particular one, namely C. So if S is the integers, so the context then is abelian groups or something like that, then Hochschild homology is often by some people called Shukla homology or derived Hochschild homology. This is a classical algebraic construction which is useful for many purposes, but perhaps most of the people listening to this right now are more interested in the case where S is the sphere spectrum. And then Hochschild homology is what's called topological Hochschild homology as devised by Bjørkstedt. But it is just the 1 sphere in the category of commutative S algebras over C. And finally, if we go to the case where S is the Matific sphere spectrum, a wonderful E infinity object, then what we get is what I call the Matific Hochschild homology of C. So that is my definition of Matific Hochschild homology. That's just the 1 sphere in the category of commutative S algebras over the C. Okay, so let's get started. So we're going to calculate.
Bjørn, I have one small question.
Yeah.
At some point very early on, you had like C tensor C op, right? But that has since disappeared. Is that because there's enough commutativity here so that it doesn't matter?
Yes, that's exactly right. Okay. So we don't see so that would be the orientation, so to say, on the 0 sphere, but we don't see that here. Thank you. Okay, so let's get started. So forget about the right-hand column and concentrate on the left-hand side. So what about Shukla homology? And we're going to be interested all the time with the prime field FP. So the 0 sphere, that would then just be tensor of FP with itself, but since everything here is derived, I not only do I get a cell in degree 0, I get a cell in degree 1, and well, then perforce, the ring structure is of an exterior algebra on a generator in degree 1. So that is Shukla homology of Fp. Okay, so the degree of tau is 1. The next level of complication is the sphere spectrum. Then C is the Eilenberg-MacLane spectrum of Fp. And you recognize the zero sphere as the dual Steenrod algebra, or the homotopy groups of the zero sphere is the dual Steenrod algebra. And I'm using here notation that will conform with what happens in the Matific case later on. So when P is even, I get the polynomial algebra, and I call the generators tau naught and so forth. And the degrees of the taus are, well, 2 times 2 to the I minus 1. And in the odd case, we have both exterior generators tau, and we have polynomial generators psi. And we're going to see later on that there is, well, these two formulas should be considered more similar than they look like generally, because the psi's here in the odd case, these fellows, I'm just trying here, these fellows should they're here as well in the p equals 2 case, but it's just so that tau naught squared is psi 1 and so forth. We'll see how that happens later on.
Bjorn, just so you know, we can see your cursor, so you can point at things without having to necessarily mark the screen. That might be easier.
Yeah, okay, so okay. I can perhaps even, yeah, okay. Brilliant. Okay, you see my cursor. That's good. Okay, so what happens when we go to the Matific sphere spectrum? Well, I'll just have to get rid of some junk here. Yes. Okay, so in the Matific sphere case, things get slightly more complicated, but not very much so. So it looks like what we had in, well, let's take the odd case first. It looks exactly like what we had in the odd case, except that we have one generated tau, which now sits on, and this is bigraded, in degree 0 minus 1. We'll get back to these grading in a moment, but for now on, it's just an extra generator here. And in the even case, we have exactly the same as what usually happens, except that we have this generated tau here. And instead of tau I squared is equal to psi I plus 1, we have an extra tau there. So it's very, very similar. The only difference is the presence of this tau. But let's get back to that in a moment and see what will happen now. So let's go from the dual Steenrod algebra to Hochschild homology, from the zero sphere to the one sphere. And if we start with Shukla homology then our ground ring is the integers. And instead of having an exterior algebra that we had from the zero sphere, we get a divided power algebra structure, and the degree of the generator is in degree 2. In the case of the sphere spectrum, something interesting happens. So then we have topological Hochschild homology of the prime field, and the answer is not divided power, but rather a polynomial algebra with a generator in the same degree. And what is good for our purposes is that these two calculations, the unknown calculations of Shukla homology, I don't know who did that, and the calculation by Böckstedt of topological Hochschild homology, they can be viewed on a common basis. So what you do is that, well, since the one sphere comes from tensoring up from the zero sphere, I can calculate that through a Tor spectral sequence. And so that will be a derived tensor of, well, homotopy groups of C with the homotopy groups of C, over the homotopic groups of the zero sphere. And here, in this case, the homotopic groups of C are just FP in both cases. So what will happen is, well, for Shukla homology, it's very, very easy, because in that case, the zero sphere, homotopic groups of the zero sphere, was just an exterior algebra on one generator in degree 1. And calculating the Tor of an exterior algebra, you can do that totally algebraically. You just take a resolution, and out pops the divided power algebra. And at this stage, well, the E2 page, there's so little going on. It's such a sparse spectral sequence. So there's not actually room for any differentials or extensions. So this is the answer. The E2 page is actually Shukla homology. So we recover my claim that Shukla homology of FP is actually the divided power algebra. And again, it just comes from a totally algebraic calculation of the Tor and the recognition that there is no room for any extensions or differentials. So far, so good. Okay, when S is a sphere spectrum, things get slightly more involved, but at the outset, it's more or less the same thing. So now the dual Steenrod algebra is no longer just an exterior algebra, but in the even case, P is equal to 2, I have polynomial generators. And again, you can just sit down and calculate the Tor of a polynomial algebra, and out pops an exterior algebra, square zero. And in the case for P is odd, then we have both exterior and polynomial generators, which Tor then just translates to divided power algebras and exterior algebras. And that's it. So this is totally algebra. There's nothing spooky going on. However, how can it be that Bøckstedt gets a polynomial answer out of this? Well, first and foremost, just look at this odd case here. If we're going to get a polynomial answer out of this on a single generator, there's got to be a lot of carnage here. So there are lots of differentials. Things kill each other in a very systematic and dramatic way. And what will eventually happen is that these lambdas here, they are suspensions of the psi's that lived in the dual Steenrod algebra. And the mu's, they are suspensions of the taus that lived in the dual Steenrod algebra. And the lambdas here then conspire to kill all the divided power structure over here. And at the infinity page, I'm left with an answer that is just like in the P equals 2 case. So the infinity page looks exactly as what I've written in the P equals 2 case. But then there are extensions given by power operations. And so the mu I here, mu I squared, or mu I to the pth in the odd situation, will then hinge up to be mu I plus 1, so the next one. And so they all hinge together to get just one polynomial generator. So this is a rather complicated story. And so that, of course, makes you think that things will go very badly when we get in an even more complicated situation. But luckily, it doesn't. So let's go immediately to the Matific case. So again, K is an algebraically closed field. We could do some more complicated cases, but let's just think of the complex field, C. And so here we're going to look at the Matific sphere spectrum, and C is going to be the Matific Eilenberg-MacLane spectrum. So just as a quick reminder, so this is the last time I'll say something about the right-hand column. So the Matific world, to us, is very easy. in addition to having the usual cells that are built out of points and the empty space, you have affine varieties. And if you then demand that the affine line should be contractible, then you have Matific spaces and put the right topology on everything, Nishnevich topology. And if you want a Matific spectra, which we do, then you just invert the projective line. Okay, so with that in mind, we immediately get the Matific sphere spectrum, and we can also represent Matific homology by means of the Matific mod P Eilenberg MacLane spectrum. And since we are over an algebraically closed field, the homotopy groups, and the homotopy groups are bigraded because we have these Matific spheres here, which mix the usual topological or simplicial spheres with the units coming from this algebraic variety here. And in this situation, the bigraded homotopy groups are just FP adjoined one generator in degree 0, -1. So it has to weight -1. And if we had some more interesting situation, we would also, at least if P is equal to 2, have more interesting stuff going on. Oh, okay, that's okay. Disregard my, what I said about P equals 2. We would have more interesting stuff if the K wasn't algebraically closed. But let's stay with this case. And so Voevodsky calculated the dual Steenrod algebra, and as I promised, in the even case, I'm sorry, in the odd case, we have just the usual situation where we have some exterior generators, tau, tau1, and so forth, with degree 2 pi to the I -1, but they also have weight p to the I -1. And we have polynomial generators psi. Exactly the same thing happens in the even case, except that we have the generators taus are no longer exterior, but they're hinged up to the xi's, just like in the stable homotopy situation, except that tau I squared is no longer psi I +1. There's a factor tau here sitting in between, but that is the only difference. And this is driven home to us very, very forcefully if we start either inverting tau or working mod tau. So if I set tau is equal to 1, then I have exactly the usual stable homotopy situation. And if I invert tau, then I get the usual dual Steenrod algebra, as written up here, the Laurent polynomials on the usual dual Steenrod algebras. And if I work mod tau, well, what happens if I work mod tau? Well, then tau is equal to 0. And here in the odd case, we get we just lose the tau and we get the usual dual Steenrod algebra. But in the even case, well, then tau here is 0. So tau I squared is equal to 0. So I get the same formula as I have in the odd case, just with P is equal to 2. So I have some exterior generators and some polynomial generators.
Bjørn, sorry to have interrupted you.
Yeah.
Can I have a quick question?
Yeah.
Say you have pi double star. What about consistence with, for example, if you work over complex numbers, weight 0, p star 0? Is it compatible with the topological?
Yes. So as I said, if I so you think of K as being the complex numbers. That's a perfectly valid situation.
Yeah.
And so what happens is, okay. So what happens if if I set tau is equal to 1, I get exactly the usual dual Steiner algebra. Does that answer your question?
Tau equals to, and it will be P star 0 in your notation.
I think he's asking about what happens in weight 0. Is that right?
Yeah, in weight 0. Exactly. Yeah.
In weight 0, you do get the dual steroid algebra, the classical dual steroid algebra, but that is not as useful, necessarily a useful observation. I think that this tau periodicity, this tau inverting is really kind of the better comparison, because that's the one that corresponds to the Betty realization functor.
Yeah, and that is just to the point. So when I say tau is equal to 1, of course, that's totally nonsense, strictly speaking, because 1 doesn't have weight minus 1. So are you satisfied with that answer?
Yeah. So in this situation, you have to invert tau.
Yeah. Yes.
Okay. That's it. Thanks.
Thank you. Okay, so let's see what happens when we invert tau. Then we do have the usual Steiner algebra with a Laurent polynomial generator added. And what happens is that the zero sphere, or the dual Steiner algebra of Matific mod P Eilmer-MacLane spectrum with tau inverted is the same as the tau inverted Steiner algebra. So I can calculate the Tor, and the only thing is that I have a tau inverted hanging around, and that flips out on the outside. So I have exactly the same situation as for the topological situation, except that I have this Laurent generator. And either stealing from Bjørkstedt or doing exactly the same calculation as Bjørkstedt does, you get that the tau inverted Matific Hochschel homology is then exactly, well, here is Bjørkstedt calculation, you get a polynomial generator, but you get the Laurent polynomial of that. So that is the only difference. But perhaps it's wise to stop for a moment and see what actually is going on here, because Bjørkstedt had extensions that said that mu to the p was equal to mu I to the pth is equal to mu I plus 1. But here, for weight considerations, the correct formula is not that mu I to the p is equal to mu I plus 1, but times tau to the p minus first. So there's a slightly different equation, but that is exactly from for the reason because we have this tau coming in, and the tau is not living in degree 0, 0, but rather in degree 0 minus 1. So we do recover exactly the same calculation as we had before. And when we invert tau, that is reasonable because then we should be very close to topology. But what happens if we work mod tau? When we work mod tau, then the dual Steiner algebra of the Matific mod P Eilmer-MacLane spectrum mod tau is exactly what I get when I work mod tau on the Matific dual Steiner algebra. And we saw for a moment ago that that is the odd primary dual Steiner algebra, of course, depending on whether P is equal to 2 or not, but the formula is exactly the same as the odd primary situation. So, of course, we have to attack the case P is equal to 2. That's the most fun, because then we get some strange mixture of the odd and even situation. So let's look at that. So now, from now on, P is going to be 2 all the time. And I don't know why I wave my hand so you can't see me. Okay. So we use exactly the same procedure, and I promised you that this was going to be somehow muddling through. We just use one tool all over the place, and we use it over and over again, and it actually works. So in this situation, now let's see what's going on here. At this place where I have placed my cursor, since I'm working mod tau, the original polynomial F2 polynomial generator tau, mod tau, is just F2. So in both these two places here, I just have an F2. And up here, well, what do I say? I said that I had exactly the same formula as in the odd primary dual Steenrod algebra. So let's look here. So there are a bunch of exterior generators and a bunch of polynomial generators. We can do this. It's exactly as in the topological odd case. The E2 page, again, by exactly the same calculation, it's totally algebraic. You get a bunch of divided power algebras, mu I bar here. The bar has nothing to do with conjugation. It is just to remind myself that I'm working mod tau. That is the suspension of the original tau generators in the Matific Steenrod algebra. And the exterior algebra I get here is the lambdas here are suspensions of the original xi's. But now something strange happens. And this is totally different from the topological situation where you had an enormous carnage from differentials, and in the end you had a lot of extensions. Weight considerations, you just sit down and you calculate, you find some strange linear combinations of filtration, weight, and degree. You find that there cannot be any extensions or differentials. This is the E infinity page. This is actually the mod tau Matific Hochschild homology of the Eilenberg-MacLane spectrum. And as Dan drove home a week ago, this is fully algebraic. So we have a lot of divided powers. Everything looks like it has nothing to do with topology. And that can be viewed, at least in the complex case, through an equivalence between modules over the mod tau sphere spectrum and BP star BP co-modules. And thank you for that comment.
Just to be clear, that's like a derived equivalence. It's derived category of BP star BP
yes,
co-modules.
Definitely.
Yeah.
Mm. So, but that is sort of fun, and I was really thrilled when this just fell out like that. But of course, I was sort of sad that there was so much noise here. There's lots going on, but it's very, very rigid. So the question is, how do I recover the not mod tau from this situation? Well, I have the localized situation when I've inverted tau and I have the mod tau, and I should be able to use some sort of Bochstein spectral sequence to get home. And of course you can do that, but it turns out that it's even simpler than that. Let's just look at what is multiplication by tau. And I do know the names for some generators okay, so M here is just short for MF2. So I do know the names of some generators in Matific Hochschild homology. And I recognize some of them in the mod tau situation. So here, this is multiplication by tau. This is just quotient from the Matific Hochschild homology to the mod tau Matific Hochschild homology. And this is the boundary operation. And the Bochstein is, of course, what you get if you use the boundary operation. You get here, and then you use the projection back again. And since we had so great algebraic control of the mod tau Hochschild homology, and well, we knew something more. We can sit down with the Tor spectral sequence. We can calculate what the Bochstein here is. We find that, well, on the suspensions of the xi's, the Bochstein is 0, but on the divided power algebras of the suspensions of the taus, well, here the index of the divided power lessens by 2 at the price of multiplying with lambda I plus 1. So it's a very simple formula. And you sit down and you calculate, and then something wonderful happens. And which reminds you perhaps of what happened before in Bjørksted's calculation. And the Bochstein is differential, so I have a chain complex of the mod tau Matific Hochschild homology. I calculate that homology, and out pops a huge exterior algebra on the mu i's. So all the divided power gammas of mu i's have vanished, and all the lambdas have vanished. I'm just sitting with a bare mu i's here. And these mu i's are old friends of ours. This is exactly what in Bjørksted's situation you were left at the E infinity page, and they were hooked up to each other for him to give a polynomial answer and for us to give a slightly more complicated situation. So we recognize this, and this is exactly the piece that is going to survive when I invert tau. Okay, so this gives severe restrictions of what can actually be the answer. So first and foremost, it implies that the tau torsion that exists in Matific Hochschild homology, the tau torsion cannot be tau divisible. That's just from the calculation of the homology of the Bochstein. And the non-torsion part then actually assembles to our old friend, the part that we got when we inverted tau. So in this situation here, it is a polynomial algebra on tau, of course, and all the mu's, but the mu's are hinged up to each other in the familiar formula. And this is then because we knew these generators and we know that they survive to the mod tau calculation, or to topology, if you like. So we should try and understand the tau torsion. And then since all the tau torsion, none of the tau torsion is tau divisible, the tau torsion is exactly the image of the boundary operation from mod tau Matific Hochschild homology to Hochschild homology. And that piece will then map injectively into the mod tau Matific Hochschild homology. So since I know the mod tau Matific Hochschild homology, I can give you a rather precise description of what the entire answer is. So here's a first go at that. Our holy grail Matific Hochschild homology sits here. It maps to the torsion-free part, which is this mirror image of what Bjørksted got. The only difference is that there is a tau here, and there's the torsion part. The torsion part by Q is mapped isomorphically to the image of the Bochstein. And the image of the Bochstein then, of course, maps injectively into this. This is the mod tau Matific Hochschild homology, but it's precisely given algebraically as a divided power algebra, tensor and exterior algebra. So what can we say about the tau torsion? So of course we know it's a submodule of this horrible thing down there, but it's not that horrible. Okay, so here goes. So I'm trying to explain to you what this tau torsion looks like. And I'm going to use one small device, and this is the only combinatorics that I'm ever going to need. I'm going to talk about certain products of divided power generators. So here is the mu n, that is the suspension of a tau coming from the dual neural algebra. And here I have taken the divided power structure to, and here is the function f. I've taken this indexed on the divided power structure. So I choose an f that has finite support, and I let yf be this product of all these mu n's to the gamma n gamma 2fn. Okay, so those are just products of things in the divided power structure. But the good thing is that these fellows, together with stuff that I know that is in the kernel of the Bochstein, they all generate the mod tau Matific-Hochschild homology. Okay, so the Bochstein, of course, is not multiplicative. So I need to take some care. It's a derivation. I need to take some care how I generate things, and this is one way of going about it. And since the Bochstein is a differential, and together with things in the kernel, the YFs generate, then the image of the boundary map of the YFs will generate the ideal of tau torsion. So together with the fellows that are not tau torsion, 1, tau, mu naught, and so forth, they will generate all of Matific Hochschild homology. So hence we know generators for Matific Hochschild homology. They're given by the taus and the mu's. The mu's, as usual, the tau is the new thing from Matific Hochschild homology. And in addition, we have these tau torsion elements. So they're all annihilated by tau. So these are new animals. These animals do not live in topology. Okay, so sorry to say that here is the degree of XF if you ever want to know. And the question is then, what are the relations? Can we say anything sensible at what are the relations between these tau torsion elements? And yes, we can, because the tau torsion is mapped injectively in the by the projection down to mod tau Matific Hochschild homology, which we do know. And and we know the generators were called XF. And they were the boundary map as applied to the YFs. So the projection down to mod tau Matific Hochschild homology of the XF is what I get when I take the Bochstein of the YFs, and I can calculate that. That just gives this formula here. What's going on here? So I lose, okay, so this delta n here, that's just a Kronecker symbol. I just want the function f to lose a value 1 exactly at n. So delta n as applied to n is equal to 1, and otherwise it's 0. So this function f minus delta n is f everywhere except at n, where it's 1 less value than f has. At the price of multiplying with this suspension of the psi. Okay, so then I know exactly what the image of XF is in mod tau Matific Hochschild homology, and I know that Q is injective. So that actually gives me all the formulas I could ever want. In particular, if I let my function have support only at one place, so it's one of these multiple of this delta n, so let's just take delta n as an example. If I take x delta n, then I get the suspension of psi n plus 1 when I take the q. And lambda squared is equal to 0, because after all, it's an exterior generator. So x delta n squared is also then equal to 0, since q was a monomorphism on torsion part. And if you sit down, you can see that this is not particular for the function with support only at n. It's true for any function. The square of any of these torsion generators is actually equal to 0. So they're all square 0. But of course, they can multiply together. So different f's can multiply together. And that can be handled rather easily if you just, okay, so after all, we know how to multiply in a divided power algebra. And if I take this YF, which I remind you what is over here, YF and multiply with YG, well, then you just sit down and you calculate in your divided power algebra, and you find that that is actually a multiple of yf plus g. So this is just addition of two functions pointwise. This is the only thing that's going to happen, except for the fact that we're going to have a number in front of it, and this is the number that we're going to have in front of it. And in particular, if the support of this is then the support of the product is the intersection of the support. So if the supports do not intersect, then the multiplication of yf and yg is simply going to be yf plus g. So that gives us explicit relations among the xf's. For instance, as I said, x squared f is equal to 0. And let's just as a test case, say, look at the example where the support, the union of the support is actually of cardinality less than or equal to 2. Support is ij, for instance. Well, then I can write the multiplication of the product of xf and fg in terms of the x of two functions that have support either just at I or at j. This function here has a value fi plus gi at I, and this thing here has a value fj times gj at j. That's the only thing. And you multiply by this horrible number in front of it. And as I have commented earlier, this is not a big number, it's either 0 or 1. But the formulas, of course, grow. Complicated ways of writing 0 or 1. And that, of course, will just build on. You'll have horrible formulas involving binomial coefficients, but there's no more mystery to it than that. And for instance, if I take the support being spread out over 3 things, I'll have slightly more complicated situations. For instance, here I've spread it over 0, 1, and 2, and then I get a cyclic permutation like this thing here being equal to 0. And just to show you an example where I have common support, but even things spread out over 3 different places, then in this case here is 1 at 0 and 1, and this one is 1 at 1 and 2, and the product of these two fellows, well, this thing here has the value 2 at 1, and this thing here has the value 1 at 0 and 2. But that's it. There's no more complications than that. And yeah, for those of you who have followed this project for a while, you will know that this is not exactly what I said before, because these huge products of zeros and 1, they tend to be 0 more often than you guess, and so I guessed wrong at a certain place. But now I know what the formula is, so it's easier to guess. Okay, so let's wrap up the entire thing. So we have an algebraically closed field of a characteristic different from 2, and if you want to study more complicated fields, then things become slightly more involved. But staying with that, the Matific Hochschild homology, so the one sphere in the category of S algebras over the mod 2 Matific Eilenberg-MacLane spectrum, well, it is given by generators tau, mu, naught, mu, 1, and so forth, and all the xf's in the tau torsion. The relations between them are that mu I squared is equal to tau mu I plus 1, and the xf's, the relation between those are measured exactly by mapping to the mod tau Matific Hochschild homology. The mod tau Matific Hochschild homology is this divided power tensor exterior algebra, and the xf's are then exactly given by the image of the boundary map of the yf's, and the formulas that you get from that are exactly then just wrapped up in this formula here. And as a fun fact, at the end, you notice that, well, in stable homotopy theory, you know that if you have a module over the Eilenberg-MacLane spectrum, then as a module, it will always be a sum of that suspensions of that Eilenberg-MacLane spectrum. But you see that that is not true in the Matific world. The Matific Eilenberg-MacLane spectrum has no tau torsion, but the Matific Hochschild homology has lots of tau torsion, so it's not even as a modulus sum of Matific Eilenberg-MacLane spectra. It's something more interesting than that. Yeah, with that, I think I'll just thank you for your attention.
Okay, and we have time for questions.
Other base fields, do you have explicit calculations over like the reals and finite fields?
I guess the total answer, honest answer to that is no. We do have toy calculations, but they're not quality checked. So the honest answer is no, but yes, you can definitely do things there.
Okay.
So I imagine that like for certain types of fields, what happens is you just end up with a little bit of stuff showing up from like the Milnor K theory, right? The Matific homology has a little extra stuff, but it kind of doesn't really matter, like, finite fields where P is congruent to 1 mod 4 or something like that. Anyway, but then there are other cases where you have like, these row element, like over the reals where, things really kind of get different because of this, the row elements and so forth. So that would be very interesting to see how this plays out in the R-Matific situation as well.
Yeah, and then of course the one strategy is to do a mod row Bockstein spectral sequence on that as well. But as again, we haven't quality checked what we're seeing.
Other questions? Well, I had a question. So, I am no expert on this sort of THH kind of trace methods world, right? But my understanding is that, one of the points, there's sort of this computing THH is sort of like the first step in a process, right? Where you once then passes to TC, and one approximates algebraic K theory and so forth. Do you see this computation as like the first step in that kind of a program?
No. So there, I don't see any reason why one would hope that. Okay, so I think so. If that program is going to work, one has to see something more than what happens in the topological case. Mm-hmm. I do not. So okay. So what happens is that. The Goodwillie tower of algebraic K theory by McCarthy and Lindenstrauss is very closely connected to the equivariant remnant of topological Hochschild homology, akin to topological cyclic homology. I don't think that will pan out in the Matific world. It is quite likely that you will need the GM to play a closer role, not only the topological spheres, but also the Matific spheres more seriously. So I think the Goodwillie tower will, well, you will have to look at a slightly different gadget. And okay, so and apart from that concern, I don't see a reason why any of the standard proofs that we use would work in this situation here. So can I say it in this way? I think topological Hochschild homology and cyclic homology would be interesting in their own right for what they have to say about Matific commutative ring spectra, rather than being an approximation to K-theory.
Okay, great, thanks. Other questions? Okay, if not, I will unmute everyone so we can thank him one more time. Okay, and we will wrap it up here for today. The regular eCHT meets again in 2 weeks. However, it is possible that we will sort of add additional events to the schedule. So, check your email. We'll keep you posted on that. Okay, thanks everyone. Bye.